So, hi everyone. We're having today Visu Makam who's gonna be talking about exponential degree lower bounds for invariant rings. Yes, so I'll let you start whenever you're ready. Thank you.
So today I'm going to talk about a result of mine with Harm Dirksen, and it's somewhat of a negative result, which is familiar to complexity theorists and computer scientists in general. At the same time, it's not really a barrier result. So I want to explain. I want to explain, in some sense, more the techniques behind how we get at some of these at this kind of a result. Uh, but I will tell you a little bit of the motivation and where and why such a question is asked. And so I know there's a lot of this audience uh, who have not grown up with algebra like I have. But at the same time, I know that over the past 4 months, you have been introduced to some amount of algebra, and in particular invariant theory. So at least many of these things that I'm telling you, it's at least not the first time you've heard them. So hopefully that makes it a little bit easier to follow. Uh, but as always, it's a mixed crowd. So if you don't understand something, or if I say something that I haven't defined properly, stop me. And I guess the only other thing you should do if you're not completely familiar with some of the technicalities is ignore them. That's a good way to get in. So I'm going to give you my motivation for this. And this somewhat aligns to a certain extent with Ketan Mulmale's motivation, at least in this project. And this goes all the way back to Hilbert. But the basic setting is, again, you have a group that's acting on a vector space, and then you have these technicalities. The group is reductive, and the representation is rational. Just forget it for now because I'll give you examples, and then you only have to worry about those. Well, actually, let me give you an example right now for you to keep in mind. And the example that I'll give you is the group is SLN cross SLN cross SLN, and it's acting on three tensors, Cn tensor Cn tensor Cn. And how is the action? Each SLN is going to act on the corresponding copy of C to the n. Okay. Now, when you have such an action, you naturally associate these things called invariant polynomials, which I'm just going to write this down. So that's actually, let me go this step by step. So if I write this is polynomials on V. This is again not a big concept because basically what this means is your vector space is going to be C to the n if you choose a basis, and then this set of polynomials is going to be polynomials in n variables, where if I have a polynomial in x1 to xn, I can evaluate it at a point in C to the n just by plugging in the coordinates for x i's. Okay, that's what it is. But by writing it in this way, I don't want to pick a basis. There are good reasons to not pick a basis, but it's not going to be particularly important here to pick either of these views and stick to them. So feel free to choose whatever you like. So you have the polynomials, and then I'm looking for invariant polynomials. So these are going to be polynomials so that whether I evaluate them at some point or whether I evaluate them after applying some group element, you're going to have the same value. Okay, and there are some landmark results, but these date back a century. These are like a century old results. Landmark results is and again, these are some things that you might not think about quite that. It might not strike you the first time you look at these things, but of course, if you've been learning about rings for a while, this is a non-trivial result. Is that invariant rings? Okay, so by which I mean this guy that I wrote like this, are finitely generated. And so there's two things here. First is I've written this invariant ring as a collection of polynomials that satisfy some properties. It's not clear that it's a ring. At least I didn't tell you that it's a ring, but you can check it out for yourself. You add two of them, you're okay. You multiply, it's fine. So it does form a subring. But subrings of polynomial rings need not be finitely generated. And if you've ever heard the word Noetherian, this is exactly why that word basically came into existence. But invariant rings have this nice property that they are finitely generated under these technical assumptions here. Okay, which of course, for example, is satisfied by something like this, by this tensor action. So this is due to Hilbert, and well, okay, maybe a little bit more had to be done after Hilbert, but the idea goes basically back to Hilbert. And so, even before Hilbert, what are the questions that people asked about invariant rings? And the questions that people, okay, and the questions that people sort of asked about invariant rings are, what are the generators? And then the second question you would ask is, can you give me, well, okay, maybe I put it as 1 prime. Can you give me a minimal set of generators? And then the second question would be, can you tell me what the relations among the generators are? And the question is, why do you ask these things? Because you want to understand what this invariant ring is. And how do you understand a ring? Well, the way to understand a ring in the most naive form possible is generators and relations. So that's what they were trying to do. And this is of course a very rudimentary approach to the subject, or at least a very early motivation for the subject that goes back to the 19th century, even before Hilbert proved that these things were finitely generated. Because, I mean, irrespective of whether you prove it or not, if you try to find it and you find a finite number of generators, you still succeed. But then, I think soon after a while, people started realizing that writing down generators and minimal sets of generators and relations among them, that these can be pretty complicated. Okay? So you realize over several decades that, okay, you can do this for small cases, you can do this for some small cases, and I would also like to say some moderate cases, although everything is small if you're a complexity theorist. And then you also realize that it's pretty difficult to do it in general. And you start wondering why. And then several decades later, complexity theory comes into the picture. Okay? And then several decades later, you get an influx of complexity theory, or even more than complexity theory, really just computers and our understanding of what it means to compute things. When you realize things are getting hard to compute, I think it's natural to ask how hard to compute, right? So it's natural to ask how hard to compute. And I think like since the 1970s and 75, 1970s and 80s, people have been looking at these questions. They didn't formulate them rigorously in terms of a computer scientist's perspective, but they were trying to find generators and relations. They were trying to write programs. They were trying to make these algorithms as quick as possible, both in terms of what a human can do by hand, as well as being able to throw it into a computer as much as computational power allowed you over the decades. Okay, so this is the question that we were looking for, and so we now have kind of more rigorous notions of what it means to be computationally easy or hard for an invariant ring, and I will refer you to maybe I'll put it here. I will refer you to GCT5 Mulmulay's paper if you want to see exactly what it means to be how hard or easy it is to compute these invariant rings. But I'm going to start with a very naive measure of how hard or easy it is to get a computational handle on the invariant rings. Okay, so a naive measure of computational hardness is so-called degree bounds. And here's the degree bounds, and I mean it's a little bit of an unfortunate notation, but I'm going to stick to it just because it's familiar to me. So it's degree bounds. So it's really saying give strong bounds. By say strong bounds, I mean both upper and lower, or understand what the asymptotic nature of these bounds are for, remember you have the group acting on V, and so I call this thing beta, but you could call it anything. I cannot tell why in the 90s or 80s people pick beta. So it's the smallest integer, so that if you look at all the invariants of degree at most d, those form a generating set for the invariant ring. Okay, so one step that you've already gone past is you've forgotten about minimal sets of generators. Maybe you don't care how minimal they are, but you do care how large a degree you have to go up till before you can find all the generators. So if I told you, for example, that that the invariants of degree at most 10 are a generating set, then you could brute force search all the way up to degree 10 for all the invariants and find yourself a generating set, and then you could prune out and get yourself a minimal generating set if you so wished. Okay, so at least you have somewhere to start, and I think that's the so maybe that's something I should tell you. If I gave you okay, forgetting about how long it takes for you to do any of these things, if I asked you to find the invariance of degree 17 for a particular action, you could do it. It'll come down to a linear algebra computation. Okay, it's possible to do it. But if you don't know how high to which degree you have to go to find all the generators, you would never know when to stop. So in that sense, having a bound at all is necessary for any sort of algorithm to be able to stop. Okay, so complexity aside, degree D invariants are computable. But without a bound, without a degree bound, cannot get, at least naively, an algorithm naively to compute generators. And that's why you want something like the degree bound. Now, historically, we have a couple of results, and I think this is the fact that it's finitely generated means that beta of GV is less than infinity. That's something we go back to Hilbert, tells you there is an algorithm if you can find that bound. And then in the 80s, Popov did some work and he got a bound that's going to be about 2 to the 2 to the n. Well, okay, so I have to really tell you, if I put an n there, how is n related to this group and vector space and so on? But I mean, so there are ways to tell you what this measure is, but if you go back to the example here, right in the beginning, you think of it as that n for this tensor action. Okay, in general, there's a way to measure the input of the group and the vector space, and then that's the input size you want to look at. So Popov gave this kind of a bound, which is kind of really big, computationally not very useful, not even for something like n equal to 3 or 4 or 5. It starts getting really hard to do anything. And then Dirksen in about 2000, he gave something that's a little bit better. It's 2 to the poly n, which is still okay. And I will tell you what the difference between 2 to the 2 to the n and 2 to the poly n really is in terms of what we want to do. So you want to capture these generators of invariant rings. So you want to be able to write down these polynomials as circuits, formulas, whatever it is. And these polynomials have degrees. And if that degree is 2 to the 2 to the n, you couldn't do it with a polynomial size circuit. Whereas if that polynomial is 2 to the poly n, it is possible to do it. It might be possible to do it with a polynomial size circuit. Okay, and I think that's kind of the big difference between a result of Popov and the result of Dirksen, where Popov's result says it's not giving you a good enough result to even have polynomial size circuits for generators, whereas Dirksen's result is saying it is now possible, but it's also hard to come up with polynomial size circuits for exponential degree polynomials. It's not always or easy to do. And then I want to mention one result of mine, with Dirksen, and this was in 2015, I think. Uh, and here we looked at what's called the left-right action. And it's going to be very close to the example that I showed you, but instead of three SLNs, I have two SLNs, and it's acting on well, m copies of n by n matrices, which you can also think of as Cn tensor Cn with m copies. So in some sense, the example that I gave you is a generalization of this guy. So this is sort of the baby version of that. And okay, so G is this, V is this. So in this case, we showed that the degree bound is at most n to the 6. Okay, so this also had a long history, and I think starting from you can put all these general bounds, and you get a 2 to the poly n, and then KV and Ivanios and Huming, they improved it a little bit they improved it a little bit, and then me and Dirksen, we got a little bit more, and we managed to make it polynomial. And there was a consequence of this, and of course it's not an immediate consequence. It needed a little bit more work, maybe from the same three authors that started this algebraic improvement of this degree bounds in this case. And one of the consequences of this was we managed to prove that we, as in the mathematical community, or the computer, the GCT community, managed to prove that rational identity testing is in polynomial time. And now there's a couple of different proofs of this. Okay, it's now a fairly old story in my mathematical life, at least. And then we realized there's a couple of things that I want to point out here. The first thing I want to point out here is that invariants in this case have this determinantal form. So what kind of it is? So you have m matrices, each of size n by n as an input. So what you do is you take like a tiling of matrix. So you take like a block matrix, a d by d block matrix. Each block is going to be some linear combination of these matrices, and then you take determinant. So it's going to look like this. Determinant of some block matrix like this, where each block is a linear combination of x1 to xm. These are the input matrices. Okay, and therefore you can see that because determinants can be computed somewhat easily, you can write down these invariants with rather small size circuits, because the degree that you have to go to is polynomial. At the same time, if this degree bound was exponential, determinant of an exponential size matrix, it would be very hard to write it with a polynomial size circuit. Okay, but of course I can't rule it out, because in complexity theory we really don't know how to rule out anything. Excellent. So, and okay, so now here's the kind of the generalized version of it. So in the left-right action, we got hold of this algorithmic problem called rational identity testing, the non-commutative rational identity testing. And in general, you have this action, and this corresponds to this thing called the null cone membership problem. We don't need to know what this is for now, but of course, I think there's been lots that's been spoken about it. And so the naive hope would be, or maybe let's not even put it as naive hope. Let's put it better degree bounds implies faster algorithms, even without telling you whether it's polynomial, exponential, whatever it may be. For what I'm going to call this null cone membership. Okay, so that's the naive hope. And the fact that we were able to do it in this left-right action, and the natural generalization of it is as tensors, which again corresponds, like there's many problems, algorithmic problems that correspond to tensors that get stuck inside these symmetries. I mean, any problem that has the group symmetry, any problem that's basis independent, invariants tend to play a role there. So you want to understand maybe how difficult it is to, so you want to understand how difficult it is to get a computational handle on the invariant ring in the next case. So the next generalization of the left-right action is where you have the group to be SLN cross SLN cross SLN, and the vector space is Cn tensor Cn tensor Cn taken m times. And okay, I'm going to wait for a. There's a question, so I'm reading it. Are there natural actions? Okay, so I'm going to postpone this question for a little bit, because we may have to argue a little bit about what a natural action really is. But I will show you that there's a lot of cases in which you are going to get super polynomial degree lower bounds. What are the consequences of that? We can chat about towards the end, maybe. Okay, so I'm not going to leave this as a suspense, but maybe I will tell you just the results that I have with Dirksen, and this is the present paper that I'm trying to talk about. In this case, so SLN taken 3 times. Actually, I'm going to renormalize a little bit. SL3n taken 3 times, and C to the 3n tensor C to the 3n tensor C to the 3n taken 5 times, 5 copies. The degree bound for this is greater than or equal to 4 to the n minus 1. Okay. But I don't want to prove this theorem for you, or at least I don't want to show you the proof of this theorem, because it gets to be notationally very annoying for me, because I have to write lots and lots of indices and subscripts and superscripts and so on. So I'm going to make my life a little easier by showing you a similar result with basically the same exact technique, but something that's easier to understand, because I'm going to write polynomials and so on. So here I look at the action of SL3n, just one SL3n acting on, I'm going to write it as sim3 of C to the 3n, 3 copies of this, but this is basically degree 3 polynomials in 3n variables. And in this case, beta is greater than or equal to 2/3 of 4 to the n minus 1. So this is the guy that I'm going to indicate a proof for. And the same technique sort of applies in that, in the notationally more complicated case. Okay. Well, maybe it's 3 copies, maybe it's 4 copies. I don't really care so much at this point. I think it's 4 copies. I mean, I can also do it for 3 copies, but then, yes. So this is the question I was expecting. What if you have just 1 copy? And I believe the answer is you should have an exponential degree lower bound, but then you will see that I will never know how to prove it, because my technique suffers from a disease that does not allow me to do it without a second copy. Okay, and you will see this pretty soon. And so the key idea that I do is going to be, okay, so maybe actually let me just be very quick about a couple of things. So I have C to the 3n. I'm going to take as basis for this entire thing x1 to xn, y1 to yn, and z1 to zn. So I need 3n things to be a basis. I'm going to choose them to be these 3. I'm going to break them up into 3 things. Makes my life easier. I'm going to do many things with this breakup. And so sim 3 of C3n is basically degree 3 polynomials in xi, yi, zi, 1 less equal I less equal n. Okay, so it's just that. And the action of SL3n on this is quite clear, because you know how SL3n acts on these basis vectors x1 to xn, y1 to yn, z1 to zn. And then if you have a polynomial, you just take every variable and replace it with some linear combination that SL3n tells you where to go to. Okay, and the idea is again similar to something that you might see in many contexts in complexity theory. It's called lifting. But here I'm going to lifting low bounds from Taurus actions. So let me tell you next the result that I'm going to use. The result that I'm going to really use, the key result, is called Groshans principle. And this was a result that was proved maybe 20, 25 years ago, maybe 30 years, maybe 40 years. I'm getting a little lost with time, but a couple of decades ago, well before anybody was interested in any of these things from a complexity perspective. And the result is as follows. So if you have a group that's acting on two different representations, V and W, and you have some point in the first vector space whose orbit is closed, okay, closed orbit. By closed orbit, I just mean G dot V is a closed subset. Then you look at its stabilizer, which is a set of all group elements which will not move the little vector at all. I'm going to call this H, just for notation, it makes things easy. And then Groshans showed that there's this kind of surjection. So you take the direct sum of these two representations and you look at the invariant ring, and there's a surjection onto just looking at the second representation and the action of the smaller group, which is the stabilizer. Okay, so let me write down one more thing and then I'll say a little bit more about why something like this is true. So what this means is you have a surjection and it sort of preserves degrees in a very natural and nice way, which means that if you take a generating set on the left hand side and you push it forward through this map, you get a generating set on the right hand side. And so if you have a lower bound on the right hand side, you get a lower bound on the left hand side. Or equivalently, if an upper bound on the left hand side, you get an upper bound on the right hand side. So what this says is that the degree bound for V direct sum W for the action of the larger group G is going to be greater than the degree bound for the smaller group for just one representation, just the W representation. Okay, so let's think a little bit about what is this surjection really doing. Well, one of the things you should think about the invariant ring is it's a way to capture sort of the quotient. So it's trying to capture, invariant rings are trying to capture the quotient. So they're trying to capture, okay, let me get this color off. We're trying to capture something like this. Okay, I put a second line. If you don't know it, forget it. Just think of it as a quotient. So you're trying to look at the set of orbits here. Now inside here, if I just look at the orbit of this space of this vector V, okay, maybe instead of putting a direct sum, I'm going to put a cross, just because after a while the two things aren't the same. So so it's just a subset, right, of which G dot V is kind of closed. But then this here, if you think about what the group action is doing here, this G dot V is sort of absorbing the G mod H action. Because the stabilizer of V is H, G dot V is basically G mod H. Okay, so G dot V is basically G mod H. And so so this guy here sort of absorbs the G mod H action. And so this guy here roughly turns out to be just W for the action of H. So the way to think of it is, when are 2 points in W in the orbit of in the same orbit for H? And the answer is if and only if. So W1, W2 in the same H orbit, if and only if V comma W1 and V comma W2 in the same G orbit. And that's the key that allows you to prove such a surjection. Okay, that's an exercise. It's not that hard. Okay, that's great. So now let's think about it. If I want to use this, I'm going to do it in two different ways. So let me write these things down again, maybe. So the setup that I have is I have G's acting on VW, little v in V with closed orbit, and I have the stabilizer. So GV is G in G such that GV is equal to V. And then I have that this degree bound is larger than this degree bound. So what I'm going to try and do in this whole thing, so the first step is going to be to identify a point in this vector space with closed orbit. So that's a challenge. You have to identify such a point, but it also has to be useful. And the second thing is I'm going to try and ensure H is a torus. And then the third thing is it's got to be weird enough that I'm able to prove ability to prove lower bound for H action. So if it's a simplistic torus action, you won't get a big lower bound. So the torus action has to be sufficiently twisted in so that you actually end up with a large lower bound. That's okay. So that's one challenge, is to pull out an H that's sufficiently, that has a sufficiently twisted action into that. But also the other challenge that I want to point out is how do you identify a point with a closed orbit? So you have to be able to prove that a certain point has a closed orbit, and then you have to be able to compute its stabilizer. Okay, so here's maybe a big challenge is how to prove that V in V has a closed orbit. And this is actually something that I want to tie up as the main motivation for the next talk that I'm going to give, which is going to be all about how can you find whether something, whether a point has a closed orbit or not. I won't give you a full answer because I don't know it myself, but I will try and do as best as I can, and I will try and do as best as I can keeping this context in mind. Okay, and maybe there's another challenge here that is kind of getting all the steps to work at once. Steps to work at once. Because you need all of them to come together to give you one bound that's exponential in nature. It's not too easy, but if you're a grad student, as I was at that time, with a lot of time to spare and crunch various numbers around, you can do it. So first, let me tell you a little bit about torus actions, right? And okay, so I'm going to try and push this a little bit through quickly because it's not going to be central to this endeavor at least. But I want to tell you why it's easy to prove this lower bound for torus actions. So a torus is basically C star to the K, and it's going to act on some vector space. Let me just call it C to the M. And so what you can do is associated to such an action, you come up with this thing called the weight matrix. And this weight matrix is a matrix that consists of weights W1 to Wm. Wi is going to be in Z to the K, and this M is the number there. Okay. Now this is kind of very standard. So if you want to know how exactly torus actions you get to this weight matrix, it's probably been said a couple of times already in this this massive program. But I can also point you to something. Now you take these, okay, and let me be precise here. So we have C1 to Cm, and let's say the coordinates are called x1 to xm, just for concreteness. And then it'll turn out that invariant polynomials are basically, I think there's a very simple way to do it. It's going to be, you look at the kernel of this matrix and you look at all the non-negative integral entries in it. So if I have such an A1 to AM, basically what does this mean? This just means sum of AI, WI is 0. That's it. And they have to be positive integers, non-negative integers. Okay, so find a non-negative linear combination of these weights that adds up to 0. And associated to that, you get an invariant monomial. And that invariant monomial is x1 to a1, xm to am. Okay. And if you understand, this thing here is a semi-ring, a semi-group, sorry. And so generators of the semi-group, come on, generators here will correspond to generators. Yeah. Okay, so I've pushed many details under the rug, but what is the end point of what I'm trying to say in this one slide, and I'm trying to push it through, is if you want to do something for torus actions, you're going to come down to a matrix. You're going to try and understand what the kernel of this matrix is, and what the non-negative integral points in the kernel of this matrix is, and so on. And this is all some sort of linear algebra, at best a little bit of convex geometry. And if you want complicated numbers to come out of it, you can sit and try and work some linear algebra out. Okay? So to try and get complicated numbers coming out of it, like exponentially increasing sequence of numbers coming out of it and things like this, is an exercise. So for example, what I want to do is I want to tell you that I can, for example, rig things so that my weight matrix is something like this: 1 minus 2, 1 minus 2, 1 minus 2. And if this is the case, then the semi-group, which is basically the kernel of W, what is the kernel of W going to be? If you really look at it, it's going to be the thing spanned by 8, 4, 2, and 1. Why? Because it's like three equations. The first equation is saying x1 has to be 2 times x2. The second one is saying x2 has to be 2 times x3. And the third one is saying x3 has to be 2 times x4. And that effectively says that there's only one thing in the kernel, and that's basically multiples of this vector here. And of course, if I extend this pattern, I'm going to get, extending the pattern. I'm going to get something that looks like 2 to the n minus 1, 2 to the n minus 2, blah, blah, blah. And if you remember that correspondence that took this element to a monomial, the corresponding monomial would be something like x1 to the 2 to the n, x2 to the 2 to the n minus 1, all the way up to xn. And then you realize such a monomial has exponential degree, and you don't have much of a choice if that's the only invariant. Okay, so that's an example of what you can do when you're faced with torus actions. It's kind of easy to generate it if you work yourself a little bit. So the next thing that I'm going to focus on is going to be, by the way, you can look this up in the paper. It's written, of course, a little bit more with a little bit more detail and a little bit more precisely. And of course, this is not going to be the example that I'm actually going to have to use in that thing. It's going to be a little bit more complicated, but it's the same idea. It's a different matrix, and then you have to do a different computation, but what doesn't really change much of what's underneath it. So the hard part is how to prove something has a closed orbit. Okay, so the hard part is closed orbit. But even before that, let me just go through the details of. Let me go through the details very quickly of how I prove this bound. So beta of SL3n acting on sim3 C3n 4 times, we said was 2 over 3, 4 to the n minus 1. So I'll tell you what the steps are, and it's going to be very very quick because I'm not giving you the proof now, but then I will see how many of these steps I can actually explain to you slowly. So the group here is SL3n. I'm going to try and fit it to the Groshans principle. So the vector space, so V is going to be 3 copies of degree 3 polynomials, and W is going to be the 4th copy. And then I need a point with a closed orbit. It's going to sound really funny, but this point is looks like this. So remember, the basis for C3n for me was x1 to xn, y1 to yn, and z1 to zn. So I need three polynomials. So I'm going to pick something inside this vector space, sim3 cn. So three tuples of degree 3 polynomials. So I have to give you three degree 3 polynomials. The first one is going to be sum over I xi squared zi. The second one is going to be sum over I yi squared zi. And the third one is going to be sum over 2 to the I xi yi zi. Okay. So each of these is a degree 3 polynomial. So each of these is in sim3 c to the 3n. And so the tuple is in 3 copies of that. So here's a bunch of claims. So the first claim is orbit of V is closed. And the second claim is going to be about the stabilizer. So I will describe a torus action. The torus action is going to be C star to the n. And so if I have T1 to Tn, it's going to act on xi as Ti, let me see quickly, Ti xi, yi as Ti yi, and zi as Ti to the minus 2 zi. And so that's an action. And basically this is the stabilizer. So this is the stabilizer of V. Okay, so I will be just a little bit careful here. So what I described to you is an action on so this is an action on C to the 3n, right? And so if you have an action, such an action corresponds to a map from C star n into GL3n, but it really goes through SL3n. And the image of rho is really the stabilizer, which is going to be a subgroup of SL3n. That's what I really mean, but don't worry too much about it right now. I just simplified it for you because next when you have to look for, so this is GV, which we called H before. So next when you have to look for the degree bound for H, you just think about this torus action and you're done. So that's the simplification. It also makes it easier for me to tell you and think, and even for myself. Okay, so that's the stabilizer. And then the third step is going to be, maybe I'll just squeeze it in here, the degree bound for this torus action, so I will call it T, which I will just going to write equal to H. Really bad, imprecise mathematics, but I'm sure you understand. The action's the same, so ends up being the same, so the degree bound ends up being the same, with sim3c3n is going to be greater than 2 to the 3, 4 to the n minus 1. So step 3, I don't want to do this for you, because at the end of the day, the step 3 is going to consist of what? It's going to really consist of trying to write down what this weight matrix is, an exercise in linear algebra, and then trying to do something about its kernel and and generators of that semi-group. Okay, it's a longish exercise. You can of course follow it from the paper. I try to make it as quick as possible in the paper because it's just a computation. You can do it. If you want to know how to rig it and you know how exactly to rig it, you can rig it. So the hard parts then are 1 and 2. So I have to prove that the orbit is closed, and then I also have to somehow compute the stabilizer, right? So the computation of the stabilizer, I'm going to try and tell you in words, kind of as simply as I can. And so it's a bunch of tricks. There's no good algorithm I know to compute the stabilizer. So I'm going to do a bunch of tricks. So first thing I'm going to do is I'm going to look at sum of xi squared zi, and I'm going to look at the space of partial derivatives. And inside the space of the first partial derivatives, inside the space of first partial derivatives, I'm going to look for the squares. And the only squares I'm going to see is going to be x1 squared, x2 squared, all the way up to xn squared. Those are the only linear terms, I mean up to scalars, right? So those are going to be the only squares. So which means anything in the stabilizer is going to have to permute these things up to some scalars. Okay, and then the same argument will tell you I have to permute the yi's up to some scalars. And then you realize that if I send x1 to some x7, then I have to send z1 to z7 with some scalars, of course, that fix it. And then I also have to send y1 to y7 because xi squared zi, that sum has to stick together. So it's, it's up to like a permutation of the i's themselves. You get to put some scalars in there. And then I took that last term, sum of 2 to the I x I y I z I, to ensure that you can't really mess around with the i's. And then it's just going to be about putting some scalars in front of the xi so that, this degree 3 thing. So xi squared zi. So the scalars that you stick to the xi and the scalars that you stick to the zi have to cancel out. And the same thing with the yi. So if you formalize this, you check it out clearly, you see that there's nothing falling through the cracks, and you realize that that's basically what the stabilizer is. Okay. It of course sounds a little bit hard going this way, but the point is, when I was coming up with this, I was rigging it so that I could get this thing as the torus, as the stabilizer. So I went backwards, right? So I'm trying to make this stabilizer. So I'm trying to introduce more and more things to get exactly this guy to be the stabilizer. Okay. And maybe one point that I didn't quite realize at that time, and I realized much later, is you can get rid of this. It's okay. You won't end up with this torus as a stabilizer. You'll end up with something, a finite group on top of it, but that doesn't bother things. It's a different story. But anyway, so you can rig things. You can get the stabilizer that you want. And then I was faced with this final part where I had to figure out, or at least why is this orbit closed? So that's where we're going to go now. So why is the SL3n orbit of sum of xi squared zi, sum of yi squared zi, and sum of 2 to the I xi yi zi closed? Yeah, this doesn't have an easy answer. So I'm going to come through it. I'm going to tell you for a few minutes where the idea comes from, and then a couple of minutes, a very quick explanation of computationally how you make that work. So the idea is, again, something that's probably repeated several times in talks preceding mine. It's the moment map. And what about the moment map? So this moment map, this is, I don't know, it's hard to tell how exactly these things are best understood. But there's this result of Kempf and Ness that says that, okay, so this moment map I'm going to denote by mu. I won't tell you where it goes from to what, okay, but not yet. But one of the results of this Kempf-Ness theory is that if the moment map is 0, so this is little v, so this is little v, if implies that the orbit of v is closed. But actually, the Kempf-Ness theorem tells you something more. The fact that the moment map is 0 will tell you that v is a point of minimal norm. Point of minimal norm in the orbit. And such a point of minimal norm exists if and only if, okay, so if and only if the orbit is closed. So the moment map tells you a lot more than you really want in this case. Here you just want to know that the orbit is closed. But I'm trying to figure out any way to show that the orbit is closed. And you can start with the naivest ways. You can try and find equations for the orbits and so on. It's an impossible task. Very quickly you'll realize it's just ridiculously hard to look at what the orbit is and try to come up with equations for it and things like this. Okay, so anything that you would naively try as an algebraist just falls right through the cracks. Very, very hard to get these things to work even in small cases. And you can never compute any of that by hand unless you're doing like a really, really toy case, which you probably shouldn't be doing. And so at some point when I was listening to some of these talks by by these group of authors, Peter, Avi, Cole, Ankit, Rafael, and so on, they talked about these moment map things. And then I realized that, okay, moment map tells you a lot of things, but in particular, it can tell you that the orbit of some point is closed. And then you realize, okay, so if I want to show that the orbit of this point is closed, okay, first I rigged it so that, the stabilizer is what I wanted and so on to get that number to come out. But then I also simultaneously rigged it so that the moment map vanishes on it. Okay. Here I lie to you a little bit. I can't take 2 to the I if I want the moment map to vanish. I have to take numbers here that are okay. So replace with numbers that are uh, that have absolute value 1. Just make sure they're different. And you can do this because you're in the complex numbers, and it's nice. I mean, it's also true that if the orbit of this point is also closed, it just makes the argument a little bit harder. Okay, so you have some of these things, and then you do it. So concretely though, how do you write down the moment map? It's not that simple to write down the moment map and try and make it work out. So concretely, okay, so let me just write this down precisely. Basically, check that mu of v, this moment map is 0. That's basically the end of that proof. But now let me tell you how exactly does one check. So how exactly to check the moment map is 0? So here I have to tell you a little bit about what the moment map is. So okay, I only have 5 minutes, so I don't feel too bad throwing some words at you that you might never that you might not like. But so this moment map, it goes from the vector space to the Lie algebra of the group, but rather it's dual. Okay, so what does this do? So it's a very simple map actually. So given some vector, it goes to, I have to give you a map in the dual of the Lie algebra. So to any element in the Lie algebra, I have to send it to a scalar. So to any element in the Lie algebra, I send it to a scalar. That's basically apply the Lie algebra to the vector and take the inner product back with the vector. It is a very simple map. There's not a whole lot of complicatedness to it. If you know what the Lie algebra is, you know that the group action on the vector space will give an associated action of the Lie algebra on the vector space by sort of differentiation like thing. And so if you take something in the Lie algebra, you can act on the vector, you'll get another vector, and then you take the inner product. Okay, it's a very simple thing, and it's supposed to somehow capture the gradient of norm. There are people who will tell you this much better than I can. So, and then if you grew up like I did, learning from Upendra, the first thing you want to do is, if you want to see that the map on Lie algebras is 0, you decompose the Lie algebra into direct sum of spaces. So, so I'm going to just come down very quickly, but this thing is called the Dadok-Katz criterion. And I will tell you what it is abstractly, and then I will tell you what it means in this particular case. So abstractly what they're saying is, come on, you break this vector space up into weight spaces. It's called the weight space decomposition. And these will seem like very, very natural things when I come back to polynomials and I show you what exactly these things are. And for any vector in V, you look at the support, which is basically the set of all weights such that it has a non-zero. So V you can write as V lambda. I don't know. We pick some indexing set, lambda and I. So I look at the support. It's a bunch of weights, and these weights are not going to be very different from the weights that I told you during the Taurus action, and that comprise the weight matrix. And the two conditions you need are, one, you need that the convex hull of the support of this. So there's a bunch of weights, a bunch of integral vectors. The convex hull of the support will contain 0 in the interior. And the second one is going to be, if two things are in the support, then alpha minus beta is not a root. Okay, maybe you don't know what a root is, maybe you already know what a root is, but the condition is that 1 plus 2 implies the moment map vanishes. So let me tell you very quickly what this means in terms of polynomials. And I won't do this big Y, I'll do a small version of it. Okay, so that will be the easiest way for you to see how concrete it is. Okay, so baby version. So I will pick the polynomial, which is going to be, okay. So the polynomial I'm going to pick is going to be x cube plus y cube plus z cube. Okay, and then I tell you that the weights, so here if you look at the support of V, the weights are going to be basically be 300, 030, 003. What are these? These are basically the exponent vectors. Okay, and you have to think of these modulo the vector space the line generated by the all ones vector. Okay, that's the support. It's basically the exponent vectors of these polynomials, of all the monomials involved. Okay, it's very simple. Now, if you can see that the convex hull of these does contain the origin when you think about it modulo that subspace. Okay, basically, if you add the three of them, you get 333. That's in that subspace that you want to kill. And then, so so the first one, so the convex hull of the support of V contains origin in the interior is okay. That's one. So the second condition that I wanted to look at, let me look at it again, is that if two things are in the support, then their difference is not a root. So in this case, at least, so here, if you remember, the action is going to be SL3n acting on sim3 c to the 3n. So in this case, actually in this case, n is just 1. So I don't even have to do this sim3 c3. So in this case, the roots are just going to be epsilon I minus epsilon j. So that's like 1 minus 1 0, 1 0 minus 1 0 1 minus 1. Okay, maybe there's plus minus here everywhere. That's all the roots are. How do I know this? Well, you just at some point you learn the root system of SLN and you know this. And now you see the difference of any two things in here is not equal to one of the roots. Okay, so 2 is fine. But then I can ask you slightly more questions, and this is going to be something that I will answer for you in the next talk. So here's a question. For the same action, consider the complete homogeneous symmetric polynomial. So I take x cubed plus y cubed plus z cubed plus x squared y plus xy squared plus xz squared plus x squared z plus y squared z plus yz squared plus xyz. And I'm going to ask you, is the orbit closed? And you realize that the first one is still going to be okay because the convex hull is more or less the same. But then the second one, now you get into trouble because if you look at the exponent vectors, say for x cubed and x squared y, and you take their difference, it's 300 minus 210, and you end up with 1 minus 10. So the difference, so you know the second condition where the difference of these things in the support are not roots doesn't work. So sometimes when you come to things like this, something like this just hurts. Okay, so what is the thing that I want to really get across in this talk is I wasn't trying to tell you, okay, look, this is all these conditions that you have that come from algebra from deep everywhere. No, the point is all of these conditions, when you extract out the real information from them, come down to something very simple about linear algebra computations or like looking at exponent vectors of monomials in the polynomial and so on. And so what I want to get across is no matter where these results really came from, at the end of the day, the computations that you have to do are very, very concrete in nature. And so no matter what these conditions were, you just had to check. If you were just sitting around trying to check this, you could check this. So tomorrow, if you won't have to ever find, if you come across some polynomial or something that you want to know whether it has a closed orbit, here's a technique that you can just check, even if you don't know where it comes from or why it's true. It's very much checkable, and that's what I want to get across. And next talk, I'm going to focus more on these closed orbits, especially in cases like this and say in positive characteristic and things like that where moment maps just don't exist. So you can't do gradients in positive characteristics, so what do you do? But also even in cases where we don't know, I have I came up with some more ideas based on Kemp's results that I will try and tell you next time. Again, we'll have the same feature where uh, the results are kind of abstract and they come from somewhere, but the computations that you need to do are very concrete and you can do them. Okay? Yeah. So with that, I'll stop.
So thank you very much for the talk. If there's, I don't know, we have time for one or two quick questions, I think, if someone wants to ask a question.
So where did you use m equal to 1 in this? M is bigger than 1. Where was it actually used?
So if I look at the Groshans principle,
Yes, so that
which I used here, right? So I want to give the lower bound on v directs on w. I'm using a lower bound on w.
okay.
So
Okay.
so I can only get the lower bound on v directs on w. So I can't make it a single irreducible thing.
Okay. Oh, because here on the right hand side you want a torus. So okay.
Yes, exactly. Something like a torus on the right hand side, and the left hand side is the one that's getting the lower bound. Okay, so maybe I can address Ram Prasad's question. So a little bit at least. So when you say natural actions when there's a super polynomial lower bound, well, this, I don't know, degree 3 action on SL3 on degree 3 polynomials seems pretty natural from my perspective. Actions on tensors seems pretty natural from my perspective. But I also want to point out and leave this as a question that I tried to pursue, and for some reason I haven't done it, is even if you just look at SLN actions, say polynomial actions, what you can basically see from our results, and I think one of the things I tried to convince you, which I maybe didn't say explicitly, is there was nothing specific about sim3 or 3 tensors or something. If I gave you 7 tensors, I could still come up with such a point and stuff like this. Okay, so any number of tensors is fine. Of course, if you go back to matrices, then you can't do it, and you will also see, because you try to follow the same thing and you'll fail. So degree 3, sorry, if I look for degree D polynomial actions, for D greater than 3, greater equal 3, I have exponential lower bounds. In general, of course, you can have some actions where you have no invariant ring or something, but in general, you'll have exponential lower bounds. For D equal to 2 and D equal to 1 is a trivial case, so we'll ignore it. And for D equal to 2, I don't actually know. And here's something I want to say. This comes down to exactly one action. SLN acting on n by n matrices, n squared copies of them, but I'll tell you what the action is. The action is G acting on A1 to AN squared is GA1 G transpose GAN squared G transpose. So what is the degree bound for this action? Is the degree bound for this action polynomial or exponential? I don't know the answer to this, but certainly somebody can. I welcome anybody who's interested in pursuing it to talk to me about it.